In this video, we're going to look at testing hypotheses regarding a population mean. So the hypothesis test for a population mean is going to be based on students' t-distribution, just like confidence intervals were based on students' t-distribution, provided that we meet the following conditions. So to test hypotheses regarding the population mean, use the following steps provided that the sample is obtained using simple random sampling or from a randomized experiment. The sample has no outliers and the population from which the sample is drawn is normally distributed, or the sample size n is large. In other words, meaning n needs to be greater than or equal to 30. So again, we need to have a normal distribution. So either we have to verify that the population is normal, or we have to have a sample size of 30 or more, just like with confidence intervals. And the sampled values have to be independent from each other. And so again, the way we're going to test that is that the sample size needs to be less than 5% of the population. So n, the sample size, is less than 0.05 times uppercase N, the population size. Now, if these conditions are met, then we're going to conduct a hypothesis test pretty much the same way we did for proportions, except it's going to be based on students' t-distribution. So step 1, determine the null and alternative hypotheses. The hypotheses can be constructed in one of three ways. The null hypothesis will be that mu equals some value, which we'll call mu naught. And then the alternative hypothesis will be mu is not equal to mu naught, mu is less than mu naught, or mu is greater than mu naught, depending on the scenario. And that'll result in either a two-tailed, a left-tailed, or a right-tailed test. Step 2, select the level of significance, alpha, depending on the seriousness of making a type 1 error. Again, you're generally going to be told what to use for alpha, but in real practice, you have to make that decision yourself, and it will depend on the seriousness of making a type 1 error. Step 3, we're going to compute the test statistic, whether we're using the classical approach or the p-value approach. So the test statistic here will be a t-naught because we're dealing with students' t-distribution. Again, same mathematical logic that we used when we were doing confidence intervals. So we're going to take x bar minus mu naught being the mean stated in the null hypothesis, divided by the sample standard deviation over the square root of the sample size. So whether we're doing a p-value approach or the classical approach, either one, we're going to calculate that test statistic. And that's going to follow n minus 1 degrees of freedom. So whatever our sample size is, n minus 1 degrees of freedom. Now, if we're using the classical approach, we need to find the critical values. So if we're doing a two-tailed test, alpha will be split between the two tails, and we'll find the two critical values. If we're doing a left-tailed test, then alpha will be the area in the left tail, and we'll find this critical value, which should be a negative t-value. And if it's a right-tailed test, then alpha will be the area in this right tail, and we'll find t sub alpha, which is going to be that critical value. Again, this is just like what we did when we were doing confidence intervals. It's just a matter of what's the area in the tails so that we can figure out what the critical value is. We're then going to compare our critical value to the test statistic, or really I prefer to say we're comparing the test statistic to the critical value. If our test statistic is smaller than the left critical value or bigger than the right critical value in a two-tailed test, we reject the null hypothesis. If it comes in between, we do not. If we're doing a left-tailed test, if the test statistic is to the left of or smaller than the critical value, then we reject the null hypothesis. If it's to the right or bigger than, we do not. If it's a right-tailed test, then if our test statistic's bigger than the positive critical value here, we reject the null hypothesis. If it's less than or to the left, we do not. That's the same exact work that we did when we were dealing with proportions. The only difference is that we're dealing with a t statistic instead of a z statistic. If we're finding the p-value, again, we find the test statistic, and then we use that to figure out the p-value. So if we're doing a left-tailed test, the p-value will be the area to the left of the test statistic. If it's a right-tailed test, then the p-value will be the area to the right of the test statistic. If we're doing a two-tailed test, then the t-value will either be negative or it'll be positive, one or the other. So we're going to find it and the opposite, so that you're going to have one negative value and one positive value, and the area On the outside of those two values will be the p-value. So again, the p-value will be double what it would be if it was a left-tailed or a right-tailed test if we're dealing with a two-tailed test. And if, once we know the p-value, if the p-value is less than alpha, we reject the null hypothesis. If it's greater than alpha or equal to alpha, we do not reject the null hypothesis. And then we state a conclusion. So our process is pretty much the exact same as what we saw in the previous section when we were dealing with proportions, except when we're dealing with a mean, we calculate the test statistic a little differently, and we're dealing with a t-distribution with n minus 1 degrees of freedom, so that works a little differently, but the concept's the same either way. So let's take a look at an example. Example. The U.S. Golf Association, or USGA, requires that golf balls have a diameter that is 1.68 inches. After hearing concerns that a new brand of golf ball might be too big, a USGA official randomly selects 40 of the new brand golf balls, measures their diameters, and finds the mean to be 1.682 inches with a standard deviation of 0.006 inches. Are the new brand golf balls too big? Use a 0.05 level of significance. So again, the process for conducting the hypothesis test is pretty much the same as what we saw previously with proportions. So we're going to start by figuring out what our null and alternative hypotheses are and what our level of significance is going to be. And then we're going to check and make sure that our conditions are met so that we can conduct the hypothesis test using the t-distribution as the model. So our null hypothesis, we're going to assume that these new golf balls meet the standard of the USGA. So we're going to have that the mean of these golf balls, these new golf balls, equals 1.68 inches. Now the concern of the USGA official was that the balls might be too big. In other words, the diameter is bigger than 1.68, so that's going to be our alternative hypothesis. So mu is greater than 1.68 inches. So this is going to be a right-tailed test. Alpha is equal to 0.05 because that's what we were instructed to use in the problem. And 0.05 is a pretty common value to use for the level of significance as a general rule. So do we meet the conditions? Well, we need randomness. So it says here that the USGA official randomly selected 40 of the new golf balls, and so we do have randomness based on that statement. We need to have independence, so our sample size needs to be less than 5% of the population. Well, clearly 40 is less than 5% of the population. And we need to have a normal distribution underlying this so that we can use the t-distribution as the model. Well, we have a sample size of 40, which is 30 or bigger, so we meet that condition. So we meet our three conditions which we need to be concerned about. We have randomness again, we have independence, and we have an underlying normal distribution that allows us to use the t-distribution. So we're good to go. We can conduct this test. So again, we have the classical approach. So we're going to show you that. And we also have the p-value approach. You need to be familiar with both of these approaches, although the p-value approach is the more common approach nowadays. So again, this is going to be based on a t-distribution. So this time we have a t-distribution. Our sample size is 40. So that means we have 39 degrees of freedom, 40 minus 1, so 39 degrees of freedom. This is a right-tailed test, and we have this area in the right tail is alpha equals 0.05. And so we need to figure out what is that critical value right there. So how do we do that? Well, we can do that several different ways. One, we can use our t-table from the appendix of the book. If you have an inverse t command on your calculator, you can use that. Or you can use the t calculator in StatCrunch. Which one you use is strictly up to you. I'm going to use the t-table from the appendix of the textbook. So the area in my right tail is 0.05, and we have 39 degrees of freedom. So I'm going to come down this column until I get to 39 degrees of freedom. And so 39 degrees of freedom's here. So that value is 1.685. That is our critical value. 1.685. Now, just for the sake of it, I could have also used my calculator, the inverse t command. So if I go to distribution and inverse t, now remember, for this inverse t command, if you have that on your calculator, you have to always enter the area to the left of the t value. Since the area in the right tail is 0.05, the area in the left tail is 0.95. And again, we had 39 degrees of freedom. And so I get 1.685 if I round to 3 places, which agrees with our table. Now I need to calculate the test statistic. So our test statistic is going to be T naught instead of Z naught, and that is equal to X bar minus the mean from the null hypothesis divided by S over the square root of N. So in this case, our X bar was told to us. We got 1.682. That was the mean of the 40 golf balls. So we got 1.682, that is the X bar, minus 1.68, which is the mean from the null hypothesis. And so we're going to divide that by the standard deviation, which is 0.006, over the square root of the sample size, which was 40. So we're going to calculate that test statistic. So, parenthesis, 1.682 minus 1.68, close parenthesis, divided by, now here we have to put the denominator in parentheses. So parenthesis 0.006 divided by the square root of 40, close the parenthesis for the denominator, and so I get 2.108. So this is 2.108. So again, if I'm using the classical approach, I would compare the 2.108 to the 1.685. Since 2.108 falls to the right of 1.685, that tells me to reject the null hypothesis. So if I reject the null hypothesis, are the new brand golf balls too big? My answer to that would be yes. The new brand golf balls are too big. They're too big for the USGA standard. Now, if I want to use the p-value approach, then I find the 2.108 test statistic, and I have a t-distribution. And so this is a right-tailed test. So the area to the right of 2.108 will be the p-value. This will be the p-value. Now again, this is for a t-distribution that has 39 degrees of freedom. So I'm going to have this t-distribution with 39 degrees of freedom. The area to the right of my test statistic, because it's a right-tailed test, will be the p-value. Now the question is, how do I go about figuring out what that p-value is? Well, I have, again, the calculator that I could use. I have the t-calculator in StatCrunch that I could use, or I could use the table. Now, I'm going to show you the table, but the table is very, very limited in its ability to help us with this p-value. So here's how the table is going to work. So what I'm going to do is I'm going to come down to my degrees of freedom, 39 degrees of freedom, and I'm going to look for my test statistic in that row. And again, my test statistic is 2.108. So I'm going to go across this row and I'm going to find 2.108, or the closest thing there is to it. Well, 2.108 is not in this row, but if this was a more detailed table, 2.108 would come between this 2.023 and 2.125. Well, 2.023 matches up with an area of 0.025 in the right tail. And 2.125 matches up with an area of 0.02 in the right tail. So what that tells me is the p-value has to be something between these two values. So the most that I can say from the table is that the p-value is between 0.02 and 0.025. Now that's not terrible, but that's also not great. So it would be better to get a p-value more accurate than that. And so we can do that again with the calculator, or we can do that with the calculator in StatCrunch, the t-calculator in StatCrunch. So let me show you the calculator. So in calculator, when we go to distributions, we have this tcdf command that I don't believe we have used before. That tcdf command works just like the normal CDF command, except we have to tell the calculator what the degrees of freedom are. So if I choose tcdf and I want to find the area to the right of 2.108, then I'm going to enter 2.108 as my left bound and a big positive number as my right bound, just like I would for the normal CDF command. And I enter the degrees of freedom, which we know is 39. So my command is going to be tcdf. As a general rule, we're going to have a left boundary, we're going to have a right boundary, and then we're going to put in the degrees of freedom. So in this case, it's tcdf. We're going from 2.108 to a big positive number, and we have 39 degrees of freedom. So this is my command. If I bring back in my calculator, now I entered that information in this window, but when I paste, I get that command, 2.108 to a big positive number with 39 degrees of freedom, and so that gives me 0.0208 as my p-value. So the p-value is 0.0208, which incidentally is in between 0.02 and 0.025, so it does fit. And because that 0.0208 is less than 0.05, we reject the null hypothesis. So again, 0.0208 is less than 0.05, so we reject the null hypothesis. So we can use either the classical approach or the p-value approach. Now I mentioned we could also use the t-calculator in StatCrunch. I can go to Stat and Calculators and T. This gives me the t-calculator. So I can enter in the degrees of freedom, which is 39. And I want to know what is the area to the right of my test statistic. And my test statistic is 2.108. So I enter that inside here. When I say compute, I get 0.0208, which is the same value that we got using the calculator. So the p-value in this case is 0.0208. So again, we have to know what to do with that. So the fact that that p-value is smaller than 0.05 means we're going to reject the null hypothesis. So are the new brand golf balls too big? Yes, the new brand golf balls are too big to meet the USGA standard. So we'll look at our next example on a new video.